Okay, thank you. All right, so today I'm actually going to go back a little bit because after looking at the first exam and just seeing how everybody did, I want to do something that it's somewhat of a simplification, but just to get everybody to understand that it's kind of maybe the best way to put it is you don't need a sledgehammer always to solve problems. So when I looked at the first exam, one of the things that was quite, it kind of surprised me a little bit is that on the first problem, it didn't look like anyone understood that there was a really big simplification that could be made in this problem in the way it was formulated when it came to using a direct shooting method. And everybody overcomplicated it, and it became a lot more difficult to do than was necessary. So today what I want to do is I want to first do this problem. If you remember the question 1 from the exam, and this is from exam 1, was as follows. It was that you wanted to minimize J, which was equal to TF, subject to the dynamic constraints x dot is equal to V sine U, y dot is equal to minus V cosine U, and V dot is equal to G cosine U, with the boundary conditions that x at 0 is equal to 0, y at 0 is equal to 0, V at 0 is equal to 0, x at TF is equal to 2, y at TF is equal to 2, and V at TF is free. Now, sorry, negative 2 here for y. Now, if you remember this problem, one of the things I asked you to do on this problem was to show, we wanted to show that u double dot is equal to 0. Now, the way you show that u double dot is equal to 0 is by forming the Hamiltonian for this system and then getting the condition for the optimal control, and then you just have to differentiate that condition for the optimal control twice. So I'll start this process off. It's not really, this isn't the main thing I'm trying to do today, but let's just go through how we actually do this, because some people had even trouble with being able to do this, which was the Hamiltonian for this problem is lambda x v sine u plus sine u, and then minus lambda y v cosine u, and then plus lambda sub v g cosine u. So we know that the optimal control, because the optimal control occurs on the boundary, inside the boundaries, is obtained by setting hu equal to 0. So if I set hu equal to 0, what's hu? hu is equal to lambda x v cosine u, right, plus lambda y v sine u, and then minus lambda v g sine u, and that's equal to 0. So if you gather terms here, this gives you that if I gather all the cosine terms and the sine terms, I get lambda x v cosine u is equal to lambda v g minus lambda y v, the whole thing times the sine of u, right? So what I did was I just kept this on this side and took this to the other side. It gives you a lambda v times g sine u minus lambda y v times the sine of u. So this tells me that the tangent of u is equal to the ratio of these things, sine over cosine, is lambda x v all divided by lambda v g minus lambda y times v, right? So what you can do from that is you can show from this that if I take the first derivative and the second derivative and I start sequentially substituting in to this using the properties of the costate dynamics too along the way, because you're going to wind up getting the costate equations. So let's just write down the costate equations for a second. So what I've got is I've got lambda x dot is equal to minus hx. So if I take minus hx, I get 0. If I take lambda y dot, it's equal to minus dh dy, which is also equal to 0. And lambda v dot is minus hv. So So if I take minus hv in this problem, what do I get? I get minus lambda x sine u. That's the first term. And then I get plus lambda y cosine u. Okay, so now what I have is I have ways of being able to manipulate the expression here at the bottom, right? Which is that if I do this just straight with the expression that I've got there, if I take the rate of change of that whole thing, so I take d dt of the tangent of u, what do I get? I get u dot times secant squared u, which is equal to, now I've got to take the derivative of this thing, right? So what do I get? I get the derivative of the numerator, which is lambda x dot v plus lambda x v dot, all times the denominator, which is lambda v g minus lambda y v. And then I've got minus the numerator, which is lambda x v, times the derivative of the denominator, which is lambda v dot times g minus lambda y dot v minus lambda y times v dot, all divided by the denominator squared, which is lambda v g minus lambda y v squared. Now, if you then go ahead and you start simplifying this expression, you can see that a lot of things in here are going to wind up dropping out. This term is going to drop out. V dot is going to get substituted in. I'm going to have V dot is going to equal G cosine U, and then I can substitute that in. This term over here, I remain, and then I get an expression here which gives me something that says U dot secant squared U is equal to this whole thing. And then I can take the derivative again. I can substitute in for secant squared U because I know that secant U is 1 over cosine U, and I can use this expression over here to figure out what the cosine U is just from the fact that the tangent is equal to the opposite over the adjacent, so then I can use that to be able to substitute in, and then I get the second derivative, and I can wind up solving, and when you're all done, you're going to get U double dot is equal to 0. Okay, so the rest of this is all basically algebraic manipulation. So now, that wasn't the main point that I was trying to make, but I just wanted to show you the procedure for being able to get it. So now we have this expression that U double dot is equal to 0, and what I asked you in this question, I have the question sitting right here, was that suppose now that we wish to solve the above optimal control problem via direct shooting, assume the direct shooting method that the control is parameterized as U of t, because from here you just get simply that U of t is equal to C0 plus C1t. And what I was hoping for, but I didn't see, was that there's a way to be able to do this without getting yourself lost in a lot of code. And I don't want the computer to be a substitute for your thinking process. All right, so now you know that this is the control, and I want to do direct shooting. There's a very nice, elegant way to be able to do this without getting yourself wrapped up in writing a tremendous amount of code. Eventually, you're going to have to solve a system of equations, but I want to show you what I was thinking about when I actually did this problem, and it clearly wasn't what anybody in this room, in this class, was thinking about, because they didn't do it this way. So here's my approach. I know that this is the control, right? It's a linear function. So therefore, I can write the following. I've got V dot is equal to G cosine of C0 plus C1t. Now, how nice is that? That's about as nice as you get. G is a constant, so I can just integrate this equation, right? So what do I get when I integrate this? I get, if I integrate this, I got V of t is equal to V at 0 plus the integral from 0 to t of G cosine C0 plus C1 tau d tau, which is equal to V at 0 plus what? Well, I've got G. What's the integral of cosine? Well, the integral of cosine is going to be, there's a coefficient in front here, C1, right? It's going to be sine of C0 plus C1t evaluated from where? From 0 to t. This is a tau, actually. So this gives me V at 0 plus G over C1 times the sine of C0 plus C1t minus the sine of C0. But v at 0 is equal to 0, right? I gave you that as the initial condition. So this just gives you g over C1 times the sine of C0 plus C1t minus the sine of C0. So I can integrate this. This is the simple calculus integral. The only thing I don't know in those equations is I don't know C0 and C1. But now I can take that one step further, and now let's look at what happens when I take those expressions and substitute them into x dot and y dot, into the other two differential equations. I know that x dot, in this case, is equal to v sine u, but v is given by that expression down there. So I've got g over c1 times the sine of c0 plus c1t minus the sine of c0, and then it's multiplied by the sine of c0 plus c1t, because I just substituted into the equation, right, into this. What do I get when I do the second one? I get minus g over c1 times the sine of c0 plus c1t minus the sine of c0 times the cosine of c0 plus c1t. So this is really not that complicated, but I'm surprised that no one discovered this. Okay, so now if I rewrite this, what do I get? I get g over c1 times sine squared c0 plus c1t, and then I get minus g sine of c0 over c1 times the sine of c0 plus c1t, and then I've got y dot is equal to minus g over c1 times the sine of c0 plus c1t times the cosine of c0 plus c1t minus, plus g sine c0 over c1 times the cosine, put it over here, times the cosine of c0 plus c1t. So now look at those two equations. If you look at those two equations, you'll see that each of those can be integrated almost as easily, not quite. We have to do one simple substitution, and we can do these integrals, which is that I know that the cosine of 2 alpha is equal to cosine squared alpha minus sine squared alpha. That actually comes from just the double angle formula. If you take cosine A plus B, you've got cosine A cosine B minus sine A sine B, and then you just substitute A and B to be the same, and you get this, right? So what this tells me is, but I know that this can be reduced, and I know that sine squared alpha is what? Well, I got cosine squared alpha minus, and I got sine squared alpha, which is 1 minus cosine squared alpha, which is equal to 2 cosine squared alpha minus 1. So what does this tell me? It tells me that, sorry, I did it the other way. I shouldn't have done it with the substitution of the cosine. So this is 1 minus sine squared alpha minus the sine squared alpha, which is equal to 1 minus 2 sine squared alpha, which tells me that sine squared alpha is equal to 2 sine squared alpha is equal to 1 minus cosine of 2 alpha, which tells me that sine squared alpha is equal to 1/2 minus 1/2 cosine of 2 alpha. So what does that allow me to do in these equations here? So therefore, I can substitute for x dot, and I get x dot is equal to g over c1 times sine squared of c0 plus c1t, but I can just use this expression right here, which gives me 1/2 minus 1/2 cosine of 2c0 plus 2c1t minus g sine c0 over c1 times the sine of c0 plus c1t. So now I can integrate this whole thing, right? I mean, I can just take all that stuff and I can put it together, and I can get an expression for x dot, which can be written like this, which you've got x dot is equal to, now I've got if I take all the constant terms, so if I take the term with the cosine and I put it in front, what do I got? I've got minus g over 2c1, that's the first term there, times the cosine of 2c0 plus 2c1t. That takes care of the term with the cosine. And then I've got minus, now I've got to be careful here. I've got minus g sine 0 over c1, and then I've got g over c1. So the g over c1 is common to both of these. So I've got g over c1, and that comes into both of these. And then I've got 1/2 minus sine c0, and then that whole thing gets multiplied by the sine of c0 plus c1t. So now you can integrate this, right? What's the integral of cosine? The integral of cosine is sine. What's the integral of sine? The integral of sine is minus cosine. So what I get is I get x of t, if I integrate this from 0 to t, gives me x at 0, and now I integrate this term by term. I get minus g over 2c1, and then the integral of cosine is sine, but there's a 2c1 in there, so I've got 2c1, so I wind up with 4c1 squared, because that takes care of this, and I've got sine of 2c0 plus 2c1t, right? That takes care of that, and then I've got the integral of sine, which is minus cosine, so I get minus g over what? Well, I get c1 squared, and then I got 1/2 minus the sine of c0, and then I've got cosine of c0 plus c1t. All right? So now I have an analytic expression for this, right? And the same thing now I can do for y dot, right? So also y dot becomes this. Y dot is equal to, well, actually, you integrate sine times cosine. Now, if you integrate sine times cosine, you can just do this one directly, right? Because the derivative of sine is equal to cosine. So when I integrate this whole thing, I'm just going to wind up getting an expression that's going to be just, this is just a product where the integral, it's, you got the integral of u dv, right? So what's u in this case? U in this case is sine, dv is cosine, right? Because it's the same expression. So if I do the substitution in here, I've got u dv, so the integral of u dv is just equal to u squared over 2. So you get sine squared. So what do you get here? You got y dot, or something to y of t. Let's just integrate it. Y of t is equal to minus g all divided by c1 squared times the sine squared of c0 plus c1t, right? That takes care of that. If I take the derivative of that, what do I get? I get 2 sine, and then there's a 2 in here to take care of that. So you get sine of c0 c1t times cosine of c0 c1t times c1. So that takes care of that expression. And then you've got what else? You've got plus. Now you've got the other term in here, g sine 0 over c1 times cosine. The integral of cosine is sine. So I get plus g sine c0 all divided by c1 squared times the sine of c0 plus c1t. And then, of course, there's a plus y at 0 in here, right? And then there's an x at 0. So now you've got two expressions that this whole thing reduces to an algebraic expression at TF. I can apply the boundary conditions at TF without any failure at all. I know that x at TF is equal to 2, and I know that y at TF is equal to minus 2. So therefore, I get the following expression. I got x at TF, which is equal to 2, which is equal to minus g over 4c1 squared times the sine of 2c0 plus 2c1 TF. And then I've got minus g over c1 squared times 1/2 minus sine of c0 times the cosine of c0 plus c1 TF. And then y at TF, which is equal to minus 2, is equal to what? Minus g over 2c1 squared times the sine squared of C0 plus C1 TF, and then plus G times the sine of C0, all divided by C1 squared, times the sine of C0 plus C1 TF, and then there's a y at 0, but y at 0 is equal to 0. So you can see here, now look at how many equations I've got. I have an equation that gives me x at TF, y at TF, and x at TF and y at TF, and I've got two constants, C0 and C1. But I also have an unknown parameter, TF, right? So how many equations do I have in this particular case? If you look at how many equations you've got, you have two equations there, but you've got three unknowns, right? Because you don't know the value of TF. So what you're going to do now is you're going to say, well, I need to figure out what TF is. So I'm going to find the value of TF that's minimum, that satisfies these two equations. But everything in here can be evaluated algebraically. So this becomes a search on three parameters with two equations, right? So I have 1 degree of freedom, which is what I need. Because if I have no degrees of freedom, then there's no optimization that can take place. So the optimization problem, when you do direct shooting, then winds up becoming this. Because I've parameterized the control to be a straight line. So basically what you wind up with is you wind up with minimize TF subject to the constraints that the first one here write this whole thing out. Let's call this equation 1. Let's call this equation 2. So we'll just make it simple so I don't have to rewrite it. Subject to 1 plus 2. All right? So let's look at this. How many equations do we have? So the number of equations, or the number of constraints, is 2. The number of unknowns is 3, right? Because I've taken into account all the boundary conditions, because I know the initial values of all of these, and I've taken into account all three initial conditions. I've taken into account both of the final conditions. Now you can see that this does not require you to integrate this on a computer. You don't have to do the integration by using some numerical integrator. You can actually do this analytically. You have an analytic expression. So the number of degrees of freedom in this is 1, right? So I've got 1 degree of freedom. 1 degree of freedom. That makes sense, right? Because if I have 1 degree of freedom, that's how many degrees of freedom I should have. I should have 1 degree of freedom, because that 1 degree of freedom is telling me that I have the choice of TF, right? If TF weren't free, then I'd have 2 equations and 2 unknowns. There could only be at most one solution to this problem that would be meaningful if this problem had a solution. So, there could be multiple solutions, but let's assume that there's one solution to the problem. And also, you know something else in here, that by the way this thing is formulated, C1 cannot be 0. Because if C1 is 0, then the denominator goes to infinity in these equations. So you wind up being able to solve it without having to get into too much detail. So that tells you can do most of this work analytically. And this is kind of what I was looking for. I was looking for this taking the math as far as you could go with it, and being able to see that in the end, you just get a couple of simple algebraic equations that need to be solved. Okay, so that takes care of that problem. Now what I want to do is I want to spend a few minutes going over the second problem on the exam, because this is the one that really confused a lot of people. So I want to go through some of the basics on this problem. Now, if you remember question 2, was this. It was J was equal to the integral from 0 to 1 of x2u dt, subject to the constraint that x1 dot was equal to x2, and x2 dot was equal to minus x2 plus u, with a constraint that u had to be between 0 and 2, and the boundary conditions that x1 of 0 is equal to 0, x2 at 0 was equal to 1, x1 at 1 was equal to 1, and x2 at 1 was also equal to 1. Okay, so now let's go through this a little bit more. Okay. Now, in order to solve this problem using calculus of variations, we need to form the Hamiltonian. So we know the Hamiltonian in this case is equal to L plus lambda transpose F, which is x2u, that's L, plus lambda 1 x2 plus lambda 2 times minus x2 plus u, which is equal to what? So if you rewrite this so that you put everything involving the control together, what do you wind up getting? You wind up getting x2 plus lambda 2 times u. That takes care of this term and the last term over there, plus lambda 1 x2 minus lambda 2 x2. Now, we know that the optimal control, because the Hamiltonian is linear in the control, so the first thing you have to recognize is the Hamiltonian is linear in the control. So the optimal control is going to be determined from the sign of x2 plus lambda 2 if x2 plus lambda 2 is not equal to 0. So we know that u star is equal to the argument of the minimum over u, in this case in the interval 0 to 2, of h, right? So what this gives me is that the optimal control in this case is going to turn out to be the following. If x2 plus lambda 2 is positive, then u is going to equal 0, right? Because that's going to minimize the Hamiltonian. So this is if x2 plus lambda 2 is greater than 0. And also, if x2 plus lambda 2 is less than 0, I know that it's going to equal 2. But what happens in the middle is indeterminate, right? So it's indeterminate. Indeterminate. If x2 plus lambda 2 is equal to 0, right? So this, of course, creates a problem. So what we have to do is we have to get into a little bit more detail, because the question is any of this going to be true? So if the control, so now we have to do the costate equations. Let's look at the costate equations, because this might be a better next step. I know that lambda 1 dot is minus hx1. So lambda 1 dot is minus h. If I take the derivative of this with respect to x1, I get 0. What is lambda 2 dot? Lambda 2 dot is minus hx2. So minus hx2. Let's take the derivative. Let's take the derivative with respect to x2, or the derivative with respect to x2. You get negative u. That's this one right there. And then you get minus lambda 1, and then you get plus lambda 2. So I know from the first one that lambda 1 is a constant. So that tells me lambda 1 is a constant, right? Now I have to deal with the fact that the situation could require that the control switch between 0 and 2, and then I have to figure out whether or not there's a possibility that there's a singular arc. So in order to do that, what you have to do is you have to say, all right, well, if the control were 0 the entire time, would you be able to meet the boundary conditions? So let's rule out that situation. So if the control is 0, and I integrate these equations, I'm not going to satisfy these boundary conditions. You can actually do it yourself, and you can see that when you integrate from 0 to 1, you won't satisfy the boundary conditions if you enforce a control of 0. So that's out. Same thing with 2. If I put a control of 2 in, and I integrate the equations from 0 to 1 across the entire interval, I'm going to see again that I'm not going to be able to satisfy the boundary conditions. So the control can't be 2 either. So it can't be 0 and it can't be 2 across the entire interval. So what we have to do now is we have to ask ourselves the question, can it switch from one to the next? Well, because it could go from 0 to 2. It could also go from 0 to what now we can see clearly is a possibility of a singular arc. Right? So the only way we deal with a singular arc is we have to figure out whether or not there's any possibility that any of these things can actually be true. Can x2 plus lambda 2 be greater than 0? So the way we do that is we can look at the Hamiltonian, and we can see that the Hamiltonian in this case has to be constant, right? So if the Hamiltonian has to be constant on this solution, we know that its rate of change has to be 0. So what we can do is we can look at dH dt, and we can take dH dt. Let's just take dH dt. What happens if I take dH dt in this particular case? What do I get? I get x2 dot plus lambda 2 dot times u plus x2 plus lambda 2 times u dot. And then I get plus lambda 1 dot x2 plus lambda 1 times x2 dot. I get minus lambda 2 dot x2 minus lambda 2 times x2 dot. So now what we can do is we can start substituting in for some of these expressions, which is that we know the expressions for x2 dot and lambda 2 dot, right? x2 dot is equal to minus x2 plus u. So I get minus x2 plus u. And then I've got lambda 2 dot. Lambda 2 dot is equal to minus u minus lambda 1 plus lambda 2, right? And then I've got that whole thing gets multiplied by u. And then I got plus x2 plus lambda 2 times u dot. I'll deal with that term in just a minute. Now lambda 1 is a constant, so this thing drops out. And I get plus lambda 1, and then I've got x2 dot. But x2 dot is equal to, again, it's equal to minus x2 plus u. So I got minus x2 plus u. So that gives me this term here. And then I've got minus lambda 2 dot. But lambda 2 dot is equal to minus u minus lambda 1 plus lambda 2. And then I've got times x2. And then I've got minus lambda 2 times x2 dot. So x2 dot, again, is equal to minus x2 plus u. So let's suppose that we look at this. Now you can see that the u's cancel out here. I got minus x2 minus lambda 1 plus lambda 2 times u. So I get minus x2 minus lambda 1 plus lambda 2, the whole thing times u. And then I've got plus x2 plus lambda 2, and now u dot. Now if you look at u dot, you can actually, we'll substitute it in just a minute, but you can solve for u dot. And then you've got plus lambda 1 times minus x2 plus u. And then you've got, if you flip the signs on this, you get plus u plus lambda 1 minus lambda 2 times x2. And then you've got minus lambda 2 times minus x2 plus u. So now you can start simplifying the expressions, because you can see that in these expressions you've got a lot of things that are going to wind up canceling out. Because in the case here, you got minus lambda 1 times u, you've got plus lambda 1 times u. So that's going to wind up canceling out. You got a minus x2 times u, and over here you've got x2 times u. So they're going to wind up canceling out. So what you're going to wind up being able to do here, this whole thing has to equal 0. So what you're going to do is you're going to be able to get expressions that are you're going to be able to determine from this what the actual control has to be. And what you're going to find when you actually do this is this case cannot be true, and this case cannot be true either. So neither one of them can be a possibility, which means that the entire solution has to lie on the singular arc. And so then from that point, if you know that the entire solution has to lie on the singular arc, you know that across the entire trajectory, x2 plus lambda 2 has to equal 0. And then from there, you could start differentiating x2 plus lambda 2 to get the control. So then you know that x2 plus lambda 2 is equal to 0. So that means x2 is equal to minus lambda 2, which means that x2 dot is equal to minus lambda 2 dot. And you can start substituting in, and you can start eliminating, and you'll wind up finding that the optimal control is going to equal lambda 1 over 2, I believe, is what it is, or minus lambda 1 over 2. And from that, you can actually determine that the optimal control is equal to 1 across the entire trajectory. Okay. So that's all I wanted to do today, because I feel like it's important that everyone sees some of this basic stuff so that you don't lose touch with the basics on these problems. It's really important that when you're doing these problems that you keep track of the very fundamental things, so that you're not just doing a lot of algebra or unnecessarily using the computer where you don't need to, where you use the computer appropriately and you don't sort of abuse the computer, because there was no need in that brachistochrone problem, that first problem on the exam, to go through and do this with a lot of integration on the computer. You could do all that stuff analytically. Okay, so we're going to stop here, and if you have any more questions on more details on getting the solution to that singular arc problem, you can come and see me. Okay.